Yeah. Having classes I gotta do, you know.
That's been working.
I prefer not. I have to do another assignment over Thanksgiving.
Done the homework, I accepted it. I was just done. Then I don't want it.
Is this final project for the lab?
No, I heard we just did the. Like,
You know about like general.
Get us started. Happy Wednesday. Wednesday is good days, you know, sunny. Actually, today we're going to talk so interesting and important topics regarding to robotics, and that's fusion. However, simple sensor fusion, but still interested. So we want to see how sensors can use. Why normally we fuse sensors?
so
Why? Can you tell me why we fuse filters as sensors? Why we fuse sensors? Yes.
because one sensor may not get all kinds of information you need or enough detail, or it's noisy. Particular.
Yes, that's right. But sometimes we fuse sensors that most of the time complement each other. So even sometimes with one sensor, we can get what we want, but we still try to fuse it with another one that give us like the same values. The main point is, yes, sensors not perfect. So we fuse them to get better estimation. That's the main point. The fusing actually is like complementing the sensors. We're going to see how this happening. A couple of tricks that we can see. So yeah, normally fusing means complement, actually completing sensors. Another point of fusing is sometimes sensors give us some information that have cumulative error. So that's actually the important part. Let's talk about this one. For example, you have a robot that doesn't use GPS, just using, for example, normal sensors like measuring the speed with hunting the wheels, an encoder. It can measure velocity and can also measure, for example, angle. This string angle, theta, for example. Based of these two and previous position, xk and xk plus 1, we want to find next step. Means x, and this is also part of that, theta k minus 1. We want to go to this state that is xk plus 1, y k plus 1, and theta k plus 1. That's the next step, state. So we can do that. Physics let us to can estimate based off the velocity and time, we can find the next position. But imagine this going more and more and more. So we are adding a little error every time. So when we measure here at the end, probably the real was much far from that. So this kind of error is important. That's called drift. This is something that we all need to know in robotics, or it's called drifting. Drifting. So drifting means that you are adding errors, you are accumulating errors, and most of the time when you are not using some sensors from outside, like GPS, for example, this happens. And this drifting is very important, and we need to fix it. One of the reasons of using fusing is actually fixing this drifting error. Okay, so drifting is very important. Let's see how we can deal with that. Normally, there is so many sensors that can get fused. For example, you can fuse IMU with wheel encoder if you want to get position. So localization happening with this. So this gives you position of the robot or localization. So in normal robots, you need to get X, K, and YK, and theta K if the robot has like a wheeling steering angle. So if you don't use anything outside, this kind of estimating called dead reckoning. Dead reckoning means just estimating the position based off previous position and normal sensing, like velocity, acceleration, time. That's called dead reckoning. Dead reckoning is very important. In most of projects that you are doing, probably you deal with that. But I did a lot. And most of actually many people do that with using control methods, but we can see without control we can do that, at least with combining the sensor. Like for example, using IMU and wheel encoder can give you very precise estimate. We can see that in action. This is one of them. So another thing that we need to learn is this dead reckoning. So dead reckoning normally is estimating the next position based on previous position and just internal sensors. So sensors that are installed in the robot to measure, velocity, acceleration. We are not getting something from outside, like a satellite or anything else, or camera. Another way of doing that is to have another camera. To that camera, give a big view of the environment and position of you in that environment. That's another way. It's like GPS. That camera is acting like GPS. But we don't have that. Imagine we don't have it. In most of the time, we don't have that. And in this case, you need to find the next position of yourself based on previous position of yourself and velocity, acceleration, and or angular velocity based off sensor like IMU or wheel encoder. Wheel encoder give you direction, you are going forward, backward, and how much going. If you know the size of the wheel, you can measure that. So you have this information. And sometimes they are complementing each other. Like IMU give the same things, but when you fuse them together, you make the precision higher. Okay, this is one that is very important. Another sensors that can get fused in this concept is IMU and IR. IMU give you like angular velocity, and IR give you distance to surrounding. If you have some information about surrounding, like there is some walls, for example, if you get those distance, you can correct next position, the next actually the position of the robot. You can correct it. You can estimate it with IMU and you can correct it with IR, for example. This is something that we can see in action today in some examples as well. Another things that you can use in terms of fusing is you use multiple sensors. Like, for example, you use IR to give you distance to surrounding obstacles, but you use lots of them. You use 100 IR for measuring distance of all surrounding, and that gives you a map, a local map of environment. That's amazing for actually moving in the environment or planning or path planning. So that's very good information. So we adding multiple sensors, we can see that another application. But else, sometimes some sensors like give you probability, like for example, touch and proximity sensors. Proximity sensors, it can be like IR2, give you distance, but this distance is not precise and it's changing, so you can compute the probability of getting close to obstacle. Or in touch is 0 and 1, is not probability, but you can approximate it as a probability. Remember, we did that in neural network with sigmoid function. You know, sigmoid function actually it's make a step function, a step function is 0 and 1, and we can make it a smoother. And this because we need kind of likelihood of collision. We want to find likelihood of collision. We can see how we can combine touch and proximity sensors to find the likelihood of collision. For object detection, for manipulators, when you have manipulators in factories that using those arms and kind of wrapping stuff, you need to use this, combining these two. We can use GPS if you have GPS, something outside like a satellite information to localize yourself. You can combine it with compass to get better localization. But this is it can be done using Kalman filter. Next class we can talk about that. And also another kind of method that can be used is like a control method using PID controller, that we're going to touch that again next class. When you have some sensors that give you some, for example, errors, you can minimize those errors. That can be done using controller. Like in IR sensors and bump sensors, you can use that as well. And some techniques that we can use, like Kalman filter, to actually make this, because we are estimating the position, localization, we are estimating the collision, we are estimating the obstacles surrounding things. So this is kind of estimation or prediction. So we need some tools for that, like what we did in neural network. In this kind of applications, because they need to be so fast, we don't need to use like learning or like training the system. This is, they can do that too, but this is separate than that. So this kind of things that we are talking in a very lower level. Information is not that much. The sensors are simple sensors, are intermediate sensors. You don't need, for example, use neural network to get a map of environment. There's lots of process for it. That's why I am talking about this part. Even though these sensors are simple, still you can get enough information to find your way to make decision, wise decision. Okay, so Kalman filter is something interesting. We can talk about that. We're not going to go deep in these things. Logic-based tree, decision tree. Decision tree is also very nice. You can say, okay, if I go this, gonna go that. If I go that, it's like a flow chart of the motion. And grid-based localization, we can have a grid of make a grid of environment and give to each grid some probability and like using Bayesian methods. That's we're not going to go deep in any of, but we're going to touch them some samples. And PID controller also and other things. We're going to talk about this next class. Today we're going to talk mostly about intermediate sensors, how we can combine them, especially in dead reckoning. Dead reckoning is, as I said, very important task in robotics. Normally we define dead reckoning as estimating the position position of the object that's moving based on previous position. And some data that coming from sensors like velocity, direction, and without any external reference. So that's called dead reckoning. Reckoning means like estimating based off now. And when we are saying is dead, it means you are not getting any external reference. And that's important because of error that happening. Because we are moving, we are adding error every time. And that error is a additive error. Additive error is the worst error that can happen in robotics. So it's additive. So the dead reckoning makes additive error or cumulative error or drifting. Okay, so the main point of using some sensors that complement each other like IMU and wheel encoder is to deal with this error. That's the main point. Let's see how we can do that. So normally the position that we want to estimate is something like that, X, Y, and theta, because most of the robots are like that. They have two wheels or maybe three wheels, and one of them is actually showing the direction of motion. If this is like the angle of the robot, this wheeling angle is theta, and X and Y is the centroid of the robot, X and Y, center. If the robot is, most of the time we consider robot as a circle. We can easily measure collision happening. We can model it like this, like a circle. Okay, so this is what we want to estimate. So the estimation part is localization. So dead reckoning is a localization method. Localization. So we want to localize the method. So what we have some angular velocity, W, that in each time slice like K, we can have that using IMU. IMU give us this angular velocity. If you multiply it by delta T, it can give you like in time. It can give you like a velocity or angle. It can give you the angle. If you add it with this theta, is give you the new theta. So the theta in time k is theta in previous time plus this angular velocity multiplied by delta t. So this is coming from IMU. So from IMU, we can fix that part. What about from wheel encoders? So we have wheel encoders. So this wheel encoder, this is the wheel. We know the size, we know this R. And also, what else we know? We know based off, because there is two, we can find omega R for right and left, because we have two, for example. And we are imagining both have the same size. And this is W left. Why they are different? Because they can be different because of noise, because of the floor type, whatever. This can be different. So we can measure velocity with actually get average from that. Multiply R by omega R, because omega multiplied by R is showing the velocity, and for left also we divided by 2 to get a velocity. So we are using actually wheel encoder to get velocity of the robot in time k. Okay, so we have velocity, we have angle, and we need x and y. So x and y also can compute. X in time k is previous x, plus when we have velocity and angle, we can compute the next next position of x. E of k, or x cos of xk delta t. We have time too, because we know in each time step how much we want to measure it in each time step. So delta t is given. And y of k is also based on yk minus 1, vk sine of delta k, theta k, and delta t. So we have omega, we have x, and we have y in time k. So this is what we wanted to compute. So based off this formula, the things that we get from these two sensors is omega k and omega r and omega l for the wheel encoder. And we knew the previous position, and based off that we computed every step, every delta t that we are moving. Okay, so any question about this? I think I have a code for that as well. Let's build this up. This is the formula. So the R is a wheel radius, and omega R and omega the angular velocity for encoders, and omega K is yaw rate for from IMU gyroscope. Okay, so, and the key idea is the IMU correct drift from encoders. Okay, they are correcting each other, of course. Okay, so example, I have this example here. So here you can see there is a, let's first explain this picture. Okay, in this picture you can see the true path is a green, and you have the blue one that is after fusing IMU with encoder. If you don't use that, if you just use, for example, IMU, it's gonna be something like, oh, I can't draw here. No. It's gonna be something like that. It's gonna be so off. I did that. I tested that in another application. You can see how off is that without correcting, because correcting is the main point in estimation. When you estimate something, you need to correct it somehow, and you need to correct it with something that is not dependent to the previous sensor. These two sensors acting separately, they are not dependent on each other. They don't have any correlation. They don't have any dependencies. That's the main point. If they are dependent on each other, we're not going to get proper correction. So in this picture, green is a true path and blue is dead reconing estimation using IMU and encoders. And those dark, the black point is a start and the red is a final estimation position. Okay, let's see the code. The main part of the code is in this part, dead reconing. So what's happening here, we are actually for the time update, yeah, we're having a loop, and here we update. Here I can type. I need to go back. Yes, here we are finding theta. Here we are finding theta. That is a previous theta plus yaw coming from the IMU and delta t, and the v that coming from averaging averaging values that coming from the wheel encoders, and the rest is computing x and y based off the the dynamic of the motion model based off the previous position and the velocity multiplied by angle and delta t. Cos of an angle and sine of an angle, of course, and then that's it, and then draw it. And as you can see, it's the precision is very good, as you can see, even though there is some errors at the beginning, but they correct each other at the end. This is good estimation, even though these two sensors not very complementing each other. They are still but still we get proper estimation of the position. Okay, that's very important. If you work in robotics, you're gonna use this for sure. Okay, so let's clean this up. Another one is touch and proximity. So touch sensor is like a 0 and 1. It's touching or not touching. But proximity give you a distance to the obstacles, for example. And this distance gets like a smaller and smaller. So it's kind of probability, but it still is distance. It's not probability. We need to change it to probability. That's actually another method to do that. We can touch that a little bit today as well. So proximity sensors detect like approaching, and touch sensors confirm that. And we can combine that together. So how we can combine that? The main thing is to find the probability of hitting object. Probability of hitting object, for example, is to so we know if you want to fuse something, we know in probability of, for example, A or B is given by 1 minus probability of A naught and B naught. So you can prove that using so many methods, like even what's the Gantt chart? I don't know the name, but you can use that. Like for example, this is A and B, and A or B can be done by, so this is A or B. A or B, and 1 minus, oh, okay, A bar or A naught or B naught. It's going to be, I'm just going to draw one to show you this is how working this the Gantt chart. In this green part is, if this is A and this is B, this green part is A naught. So imagine we have A naught and we have B naught, and we AND them together. Okay, we AND them together and we do complemented. When we say 1 minus that, we mean it's complemented. So yeah. Anyway, that's the formula. I tried to prove that, but I think it's more complicated. So let's just get rid of this proving part. But that's obvious. So I just clean this part. Okay. Anyway, we're gonna use this formula for that. We want to find, we have two things, A and B, and we want to, so A is, for example, probability of touching, like probability of proximity, and B is probability of touch. So imagine we have probability of touch and probability of proximity. Proximity means how much you are close to the objects, like close to the wall, close to obstacles. Okay? If you have these two, computing this OR is happening 1 minus probability of not be close or not touch. Okay? So so we need to compute this one. And probability of not touch is 1 minus probability of touch. Easy. Probability of, for example, touch. This is probability of not touch. Probability of touch. When I put this, it means not. Some people putting like this before, but it doesn't matter. So this means it's not touch. Okay, anyway, that's just a little probability stuff. So based off this, we can get this one. So probability of hitting object is 1 minus probability of proximity multiplied by 1 minus probability of touch. That's it. I just wanted to tell you how this formula coming from. It's just probability. Okay. So, but how we can compute probability of proximity? So because we have D, and this D is decreasing actually when you are getting close to the target. So how we can find probability of proximity? P of proximity coming from, so we want to use something like that. We want to have something smooth. When we are getting close, this is, for example, imagine it's distance. When distance get closer to this point, we have the highest probability. This is probability, P of proximity. We want something like that. Okay, this look like Gaussian, isn't it? Gaussian is like that. Imagine this is 0, and you get rid of the negative part. This is minus d. You don't want minus d. So that's why you can use actually exponential family to make that green part happening. And to get rid of the negative part, you can use this formula max of d and 0. So max of d and 0 means if it's negative, it's always 0. Okay, done. We always can add it with the noise, like 0 and some deviation, like a normal the normal noise. We can use probability of getting close to the obstacle using this formula. The exponential part coming from this picture that I show you, and that max formula coming because we don't want to have a negative distance. However, sometimes we need negative distance as well. That's called sign distance field. You want to see how much you're going to inside obstacles. So because some obstacles you can go even inside. Like for example, in self-driving cars, some obstacle you're not supposed to go. Like for example, it's a grass, it's not road, but it's still your car can go there. You can even compute that cost of going there. Okay, that's signed distance field. We call it signed distance. It's signed, but this is not signed. This is just positive. Okay, so this was a good takeout of this part. So remember that you always can use this. You always can use if you have a distance and you want to find probability of getting close to something, you can use this exponential family. Exponential families are amazing. They use a lot. What else? So what about touch? For touch, everything's different because touch is just a 0 and 1. But we learned that before in this class that we can approximate 0 and 1 or this a step function using sigmoid. So this and sigmoid function, it was like that. We can say probability of touch is equal to 1 over 1 minus e. We have some coefficient like delta d plus some noise. So this part is sigmoid, sometimes called logistic curve too. Okay, so we have these two. Okay, so let's compute the probability of collision or heating. So here is a code. To do that, you can find P of proximity and however, P of proximity need to clip between 0 and 1. So we use a function clip to do that. And find the probability of touch and clip that as well. And just multiply this. And this probability, P of object, means probability of heating object. So when you draw that, let me clean this up. You can see something like that. This red one is probability of touching, and the blue one is a probability of proximity, and the fuse one is black. So as you can see, probability of black is very close to that proximity one, but still touch fix that a little bit. As you can see, when it's going closer, it's get a little drift. However, here we don't have drift because we are not estimating or finding the position, but it still needs some correction. Okay, that was good example. The takeout of this slide is how compute these probabilities, these two probabilities. You have two type of probability. Probability that's coming from some continuous variable, that is D, because this is continuously decrease or increase. And for that case, you can use exponential families. And for kind of variables that are 0 and 1, like a discrete variables, you can use like a sigmoid function. That's important part. We have the formula here in this code as well. You can see here, that's exponential family, and this is the sigmoid function. Okay. Any question about this before moving to the next example? Okay, another example that is very good to know is how robot can get the map of the environment. One of the way of using that, using this simple robot, is to use multiple of them. You can use like 100 IR sensors to get map of environment. We sometimes call that local map, sometimes call that a spatial map. So those maps give you position of you and all obstacles around you, and the way to pass, is show you where is empty area. That's a very great point. But the main point in this kind of application is if you have so many sensors, one of the important things that you need to always do is to make these sensors all in like same space. You need to have an equal coordinates. That's a very important part. Having or making equal coordinates. That's so important. I put 3 stars. Like fixing coordinations is very important. So because they all need to be in the same space. Other than that, you can use multiple sensors if each one is in another space, in another coordination. They all need to have the same coordination. So that's why they can complement each other. If they are in the same coordinate, sometimes even you can just average them. You get a good estimation or prediction. So making same coordination is very important. In this example, we're going to see how you can get same coordination. So we have a robot, and this robot is like previous type of robots. It has a like a 3 wheels and one steering angle, that's theta, and the position is XR and YR. We are considering that like a circle shape, and we also have multiple obstacles around, and we have lots of sensors. We equip this with many sensors, and these sensors, they have some like a bandwidth and give you like a maximum distance. But if they hit some obstacles, they give you the position of that. But because the sensors installed in different angles of robot, we need to fix these positions. The positions that coming like this, for example, give you x1, y1. This give you, for example, x2, y2. This installed in, for example, angle theta 1. This is angle theta 2. This is angle 3 and they have different angles compared to the direction of the robot or shape of the robot. And we need to do this coordination or make this x1 and y1 in the same coordinate. Okay, how we can do that? There is a formula. So so that's the formula. If the center is xr and yr, so the state is xr, yr, and theta r. This phi of I is the position of sensors in the robot, in top of the robot. If, for example, this is robot, this is V1, V2, Vn, something like that. Di is what that sensor give us. This Di need to fix. So this Di need to be add with go to this formula and based off these angles get xi and yi. So this is how you can change these values to make some information that they are all have a same coordination. So the output, let I clean this up, I have a nicer picture. Output gonna be like that. So here I used 100 sensors, IR sensors, that as you can see, X's are these endpoints. The Xi and Yi are in this X point. If there is no obstacles, it's gonna be the maximum value. If there is obstacle like here, it's gonna give you those obstacles position. And that's gonna give you a good observation of the environment. You can see, for example, which area is empty for moving. So the code is here, as you can see. The main part is this part. So in this part, we are, for all angles, I consider 100. For all angles, we find the distance for that angle and then compute x, y, and y, and then draw it. Other than that, we can't do that. This is important. Okay, so yeah, I think we can do the next for the next class. Any question about this? It's some physics and mechanics that mix together for robotic. In robotic, you need to know this. Did you know these things before in other courses? Yes?
Yeah.
Like which course?
Autonomous systems.
Autonomous? Oh, okay. So they're so familiar.
Localization and then
Localization, so nice. And fusion too? Little bit too. Oh, that's great.
Dead reckoning.
Oh, okay. Oh, nice. I didn't know that. I didn't ask you before.
It's a ME.
Okay. Perfect. All right. Let's see you. Right here.
You all right?
Like